Hello, everyone. Good evening or good afternoon, wherever you may be joining us from. I'm Ahmed Khalil, and I'm delighted to extend a warm welcome to each and every one of you. Today's webinar, we will have an exciting journey to explore the Ethernet domain in the automotive applications and also in the IoT applications. Uh, today we are privileged to have an exceptional speaker, Mohamed Sallam. Mr. Sallam has over 13 years of experience in the software engineering of automotive and embedded systems. He's currently a software architect at EJAD LLC. Uh, this webinar is a part of a series of insightful sessions that we have been hosting that covered a wide range of topics to discuss and explore the software-defined vehicles, the QNX, embedded Linux, and more. If you haven't had an opportunity to explore these previous webinars or topics, please have a look on the YouTube channel and explore the old recordings of the webinars. Okay, and I would like to hand it over to Mr. Salam. Thank you for joining and thank you for volunteering to speak to the community.
Thank you. Hello, everyone. This is Mohamed Sallam speaking. I am a software engineer, a graduate of Faculty of Engineering, Cairo University in 2010. I started my journey in the automotive field almost 13 plus years ago. Back in 2011, I worked for a number of multinational and local companies here in the automotive market in Egypt. I started mainly as a software engineer, worked for Valeo, their development engineering site here in Egypt for 3 years, and then I joined another service company called EJAD, where I worked for a variety of different projects related to AUTOSAR integration, and which covered a lot of communication technologies, including CAN, FlexRay, Ethernet, and so on. And along the years, I came with close interaction with Ethernet, especially in a multiple projects, and I hope I can share some useful insights with you today. Okay, so let's start. Can you see my screen? Yes, or I think it's already seen. All right, so in the agenda today, we will try to give just a brief history of Ethernet and how it's evolved along the years. And then we will provide an overview of different vehicle functions and how they evolved also with the ever-increasing requirements and for increasing software complexity and safety standards, which affected both the vehicle architecture and the software development. And then we'll jump into the Ethernet advantages compared to other legacy and communication standards and see how it filled the gap and helped OEM, original equipment manufacturers, to satisfy both the user and the industry needs. And then we'll see, walk through the Ethernet communication layers and how the Ethernet fits into this AUTOSAR communication model. And lastly, we will try to cover one of the major, or some of the major and most important Ethernet applications in the automotive world. And then we can have a vast look in the future and see how the vehicle architecture will continue to grow over the coming years. All right, so starting from the mid and late 80s, this is where the first versions of Ethernet appeared, commercial versions, and these were product of a development effort of the founder, what is considered the godfather of Ethernet. His name is Robert Metcalfe. He and his team were working for a company responsible for doing some research and development projects, and as a result of that, the first commercial versions of Ethernet were released in the market, and those were a little bit different than the modern version of Ethernet that we know today, because these were basically based using coaxial cable as a physical medium, in contrast to twisted pair Ethernet. Later, or a few years after, maybe actually simultaneously with the outbreak of the internet at the early in the 1990s. As I remember, the World Wide Web became commercially available to the public in 1991. So we started to see more demand for higher speeds and more flexible networks, and some alternative physical mediums to try to cover some of the defects that were present in the original versions of Ethernet, as we will highlight shortly. So this is where the Twisted Pair Ethernet came into the picture. In 1988, it started with a basic version that supports 10 megabit per second communication baud rate, and then it followed with an upgrade to the fast Ethernet standard, which supported 100 megabit per second, and it's given the code name 100 base TX. And if you focus on the Twisted Pair development over the years, which is marked by the blue circles here in this timeline, you'll see that it started to quickly evolve over the time. So we saw by the end of the 90s, the first gigabit version, 1000 base T gigabit per second Ethernet for Twisted Pair. You see always when you have these code names, base -T stands for Twisted Pair. And we quickly saw most frequent upgrades. So by 2016, for example, we reached 25 gigabit per second and 40 gigabit per second. And along the way, we started also seeing some developments for Ethernet for automotive industry. The first standardized version for Ethernet came in 2015, which supports 100 megabit per second. And the code name for this standard is 100 base T1. That's basically the main difference between the standard for automotive physical layer. It would end in T1. However, the standard or normal twisted pair cable for other applications would end just base T, not T1. The automotive recent and the most recent publications related to physical layer was released in 2020. And this basically lay out the foundation for the multi-gigabit communication range, which basically covered the 2.5, 5, and 10 gigabit per second physical mediums. If you see also the fiber optics, although this might be a misconception that the fiber optics was only developed in recent years, actually it started developing as early as the Twisted Pair Ethernet. So it started in the 1998 with the first gigabit version of for Ethernet over fiber optics, but it has been ever developing in a faster rate, even not shown here in the timeline, because in this timeline, by the way, doesn't cover all the publications that was released that were released by the IEEE task force. All of these publications are part of the 802.11. That's a mega project. It was initially launched to standardize the specifications related to LAN networks, local area networks. But over the years, it started gaining much more interest from different commercial parties, and we actually started developing a lot of specifications for other mediums other than the LAN itself. So we started seeing more specifications for wireless communication, for example, and fiber optics, and other communication mediums as well that supported other industrial applications, for example, the backplane or Ethernet over printed circuit boards, for example. Just most recently this year, in February 2024, the IEEE task force agreed on the specifications for the 200 and 400 and 800 gigabit per second fiber optics over multiple lanes. Of course, such high speeds you will not encounter in default LAN setup. Those are mainly intended for covering wide geographical areas, for example, metropolitan areas, entire cities, or even entire nations. And those high speeds are designed mainly to establish high speed links with much more accuracy over long distances, maybe that would reach 20 or 40 kilometers. Right, so that's brief history. I think it's also helpful just for to have how the different cables evolved for Ethernet over the years. Those coaxial cables mainly were used for the 10 base 2 and 10 base 5. And those were, as I mentioned, the early versions of Ethernet, which are considered obsolete nowadays. They are no longer used in industrial applications. So this is the 10 base 5. It was a thick coaxial cable, which was very difficult to handle, by the way, and extending the network nodes and adding more nodes and network capacity was always accompanied with a lot of issues. It was upgraded to the Ethernet, which came a few years later in 1985, mid 80s, and then quickly replaced or upgraded to the twisted pair Ethernet, which is the version that we know today, and it supported a lot of physical different communication speeds over the years. And in parallel, also we have the optical fiber cables, which are also called SFP plus modules. SFP stands for Scalable Form Factor Pluggable. That's a fancy name. That's it has some reasons, of course, behind the name, but it's basically uses optical fibers inside the cable, which are isolated from each other, and it uses laser beam pulses to transfer or de-encode the binary data. Of course, since it's using light, then it couldn't. Nothing can beat the speed of this as a physical medium. All right, here is also a quick example of different standards maintained by the IEEE task force for this project. You have here, for example, what's highlighted here in yellow blue. This is 802.3CH. This is the standardization for the physical layer specifications and management parameters for 2.5, 5, and 10 gigabit per second, which is of course used only in automotive electrical Ethernet. The green one, 802.3AN, this lay out the specifications for multi-bit gigabit per second over normal twisted pair. And the difference between normal twisted pair and automotive twisted pair is mainly the number of channels used or the number of twisted pairs inside the cable. The automotive, you'll see that it's always use one single pair, and that's due to the restrictions inside the vehicle body not to use bulky and complex cables, because this will add not only to the cost of the manufacturing process, but also to the handling and maintenance and overall production cycle. So it's always there's always a stress to push towards supporting different communication speeds over the same single twisted pair for automotive applications. But in other industries, for example, IoT or other Ethernet-based communications, you have the flexibility to use more than one channel. Without going into these standards, I just put them here for reference. For the full list of standards, feel free to visit the IEEE 802 webpage. Basically, they have dozens of such standards, and even though the original standards is released in a specific year, you'll see always that it has a lot of amendments released in 1 or 2 years later. So basically, there are dozens of standards maintained by this IEEE mega project. And also, of course, not to forget the 802.11 substandard used mainly to maintain the Wi-Fi, the communication over Wi-Fi as a physical medium. What's basically need to be highlighted here is that the Ethernet as a communication technology depends not only on the nodes participating in the network, it needs also some special type of devices, which are the switches and routers. We'll try to cover the functionality, of course. We will cover the functionality of the switches already in a few slides later. But what needs to be highlighted here is that this core device at the heart of the switched network brings multiple advantages to the Ethernet compared to legacy communication systems, because you have specified and dedicated links between each node in the network and the heart of the network, which is the switch. In this way, it is more like a star-shaped or tree-based structure. And this brings some advantages. For example, it brings multiple collision domains instead of one big single collision domain, which is usually the case in shared bus topologies. And due to this, any fault in one of the links um, at one of the switch ports would not or should not affect the other links. That's one big advantage. And due to this, also, you are able to establish mixed speed configurations within the same network. And this is not possible in other classical technologies. For example, the CAN and FlexRay, all the nodes in the network have to communicate and agree upon one single wave communication and one single speed. But in the Ethernet, you are able to support different physical mediums and different communication speeds within the same network. And this is, of course, comes at a little bit complexity in the data link layer, as we will see later, as the switch itself has to be a little bit smarter and provide some means to for the communicating nodes to establish or negotiate on the speed they want to communicate with and publish their capabilities, for example, in terms of half duplex, full duplex communication, and so on. So that's roughly an overview of most widely supported standards today that cover fiber optics and twisted pair. And as I said, you can easily look up all the lists if you're interested on the internet. All right, so let's try now to understand how the vehicle functions evolved over the year and how different factors helped build motivation for adopting Ethernet in the architecture of modern vehicles. Okay, so vehicles or cars have already succeeded in providing the basic value that were designed for, which is moving passengers from point A to point B. This has already long well established. But what we have witnessed over the years is that there has always been more pushing towards more drivers, more user comfort features. There have been more push and acceleration towards more safety features. And this turned the vehicle from a closed system into an open system that's continuously monitoring the outside world, that's always taking the outside world as a part of the operation of the vehicle itself. So in contrast to old versions of cars, or we have the modern cars that are equipped with a huge number of sensors. You have ultrasound sensors mounted alongside the vehicle body. You have short-range radars, long-range radar, which provide vision to the car, basically to try to monitor the surrounding vehicles and the surrounding environments, and most importantly, the pedestrians in the road around you. And through the measurements of such sensors, you're able to establish more smart decisions in terms of when exactly to respond to user commands in a more safer way. So you might be able even to override the user command by forcing an emergency brake signal when required. So the ultimate goal of this, of course, is human life. But as these functions turn to be more and more complicated, we start to see much more baud rate needs inside the vehicle networks because of vast amount of data that's being communicated across different vehicle domains. And this resulted as well in much higher meshing structures inside the network. So there is always more and more sensors needed, and this translated into more baud rate inside the bus, and communication buses also had to adapt to more additional nodes. Cabling harness inside the vehicle began to be more and more complicated, and the utilization of the network bandwidth was being pushed to its limit at this point due to this high nature of distributed system inside the car. This is one aspect related to the functional safety and the ADAS domain. Another aspect also is related to the movement towards e-mobility. Of course, all of this in the recent years, apart from even the vehicle industry, there has been ever and ever concerns raised due to the greenhouse consumption and greenhouse gas emissions worldwide, which resulted from different industries. But the main contributions to these greenhouse emissions were mainly being the electric usage of electricity, with roughly around 30% of greenhouse emissions worldwide, followed by a number of industrial applications, and a huge contributor also was the road vehicles. So the direction here was to try to eliminate, or at least minimize, these road vehicle emissions by depending on renewable sources of energy. We could debate a little bit here, because the electricity used to power electric vehicles at the end of the day could put more and more pressure on electric vehicle network if the energy sources themselves are not renewable. But the takeaway from this is that the OEMs will always try to produce electric vehicles which contain around 80% or 90% of their materials in that could be renewed or recycled. And the electric batteries themselves could be used somehow even in different applications other than the automotive, because at the end of their lifetime, around 70% or 80% of the vehicle capacity, of the battery capacity, would still be usable, but not really useful for the vehicle itself, but could somehow be utilized. So we will cover this vehicle to grid in more details, I think, by the end of the session. And not to mention here also, as the vehicle began also to communicate with the outside world, it was no longer an optional feature to quickly react to security concerns or the detected vulnerabilities. So the OEMs had to provide continuous series of updates over the air. This was now not an optional requirement, and to make sure and enhance the overall passenger and user safety of the car. Okay, this when it comes to the vehicle architecture, as we will highlight in the next slide, with the increased overall software size and increased complexity of the software, we started to see more and more pressure on the service line in the factoring and manufacturing process, whether to adapt to this increasing number of ECUs, which is accompanied by much more complex hardware and meshing structure. And this put also a huge pressure on the production service line to be able to perform software updates quickly. So we needed more scalable mode of operation, okay, to be able to adapt to this high levels of software complexity across multiple vehicle domains. And simultaneously, we needed to make sure that all of these software high-level functions still can be able to operate within real-time constraints that are required as part of the vehicle functions. Okay, this is a quick glimpse of how the vehicle architecture has been operating in the current vehicles. This is, let's say, pre-2022. This basically represents the current vehicle architecture. This is a highly meshed architecture. As you can see, each ECU, when it requires direct access to a certain sensor or peripheral, it needs to extend the communication bus directly to it. So this increases the complexity of network topology, and of course brings more complexity for all the production line processes in terms of software updates or maintainability, software validation costs, and so on, because testing a single feature here means covering and validation of not only the hardware, but the hardware and software of different ECUs across the vehicle network. So in order to simplify this, there has been a growing trend towards usage of what's known as domain controllers inside the vehicle. And domain controllers means these are special type of ECUs that are responsible for that act basically as a gateway to a number of local controllers working together um, to establish a specific vehicle function under a certain domain. For example, you could have domain controller for chases, you could have the domain controller for powertrain, and so on, body and comfort, and so on. The shift towards central domain basically means more scalable and centralized software development. Instead of, this is in contrast to the current trend here in vehicle architecture. So we try to bring software features that are related to each other and scattered across different ECUs under one domain controller, and this domain controller will basically hold the high-level functions while low-level activities can still be performed in these local controllers. And this is considered the first step towards software-defined vehicle, because when you think about it, when you try to introduce a new feature that on the vehicle level, this can easily be reflected and translated into underlying vehicle architecture. By usage of this domain controller, also you bring more isolation to the internal communication within the same domain, and this could also reflect on the overall security. And you, not to mention here also, since you have centralized the high-level feature development under one domain area, then this will definitely makes the software or feature updates more easy, because in the context of over-the-air updates, you now required only to update part of the car in single domain if needed, instead of trying to make software updates into multiple ECUs scattered across the car. So this is a central domain focus, and the zonal focus even brings much more simplified wiring and connectivity, and I think we will cover this zonal architecture by the end of the session in much more detail. All right, so I think we can now try to understand this, based on the concerns and the overall trend of where the ECU, where the vehicle industry was going, the need for much more higher bandwidths. We can easily understand how the motivation for using Ethernet was built all over the years. If you compare it with classical communication technologies, it can easily overshadow them. For example, the Ethernet brings tenfold the default speed of CAN and FlexRay. FlexRay maximum speed, for example, is 10 megabit per second. The CAN, classical CAN, maximum speed is 1 megabit per second. Maybe it can be extended to 2 or 5 megabit per second if you enable flexible data bit switch, bit rate switch, sorry, CAN-FD. But still, that's nowhere closer to 100 megabit per second, which is already well established outside the vehicle industry. One of the advantages of using Ethernet that pushed and accelerated the adoption of Ethernet into the vehicles also is that the Ethernet is already a well-established technology. There has been already a lot of R&D and commercial products and a lot of investments in it along the years, as we have seen. It's already available since the 1980s. So it enables, of course, opens an entire field for faster flashing, over-the-air software updates that could be applied basically from the comfort of your home. You no longer need to drive your vehicle to the service line center to receive the software updates or remove any vulnerabilities that had been discovered. And compared to the IPs needed to upgrade existing CAN or FlexRay controllers, Ethernet can actually be considered on a mass production level to be much more cost efficient than CAN and FlexRay controllers, which are considered relatively complex. So that's for all of these reasons, the automotive world start using the Ethernet as a way to move forward. All right, I want to talk now about the AUTOSAR standard layered architecture, and that's a very common standard that has been present in the automotive for over now 15 years almost. And AUTOSAR basically provides a framework for developing application components independent from the hardware. And this is possible by dividing the overall ECU functionality into different specific layers. And you have to classify the overall activities or routines done by normal software components into activities that are hardware related. So this basically will be covered in the drivers layer, and much more, a little bit higher or abstracted services from software components perspective. So each software component, for example, will need services to read and write from NVM, non-volatile memory. It will need services to run using schedule triggered or on event based triggered, and that's where it needs to utilize the system services. And each component as well will need to use some of the communication services available to its from its under layers, sub layers. So that's why the AUTOSAR have provided communication service modules such as the COM or BDR that helps the higher level applications to be not to be concerned with the dynamics of routing the different signals back down until to physical layers, which is actually supported by the microcontroller. So this model has been well established and widely used in the automotive world, and there is already different tools that support modeling AUTOSAR systems and RTE code generation. Okay. So there has been multiple specifications for the AUTOSAR over the years. The very first version that, or let's say the first version that started using or adopting Ethernet was released back in 2009, which was AUTOSAR 4. And back then, the Ethernet were not introduced with full specifications and standardized APIs, but rather than COTS or component of the shelf. So this gave the tier one suppliers the freedom to use whatever implementations they have, whatever legacy perhaps or custom-made implementations, just to support interfacing with Ethernet to the outside world. The very first specifications for the Ethernet and the TCP/IP stack came in 2013. And alongside with it, we needed also to support some modules or some extensions in the AUTOSAR to provide means for this service-oriented communication, as we'll see shortly. So there was some modules added also, what we call service discovery. We'll cover it also at the end of the session. And in 2014, another version was released, 4.2.1, which added more and more support to Ethernet communication by providing a way to standardize configuration of network topologies by Ethernet switch drivers, APIs. Also, there was support for IB version 4 only before this specifications. So IB version 6 was added. And for time-sensitive applications, some new, not new standards, I would say some already existing standards that are used in the Ethernet outside the automotive world have been adopted in the AUTOSAR. So time synchronization using BTP protocol, precision time protocol, for example, has been specified here as well. And this SOMEIP transformers I will cover in a few slides. And this is really necessary to bridge the gap between the old communication mechanism used in AUTOSAR and the new Ethernet way of communication. All right, so if we have a look at the legacy communication stack in the AUTOSAR used by the AUTOSAR, we had mainly systems which had tight coupling between the high-level signals that needed to be sent and transmitted by the applications and the lower layer frames that exist on the bus. So as mentioned before, the AUTOSAR intended to classify the communication needs of different layers and try to somehow decouple the different activities done in different layers by providing standard specifications for each modules and putting and describing exactly the behavior that should be followed to be able to route the communication elements or signals from higher layers down to the physical controllers. So in this way, we found some essential modules at the heart of the communication stack. For example, the BDU router. And this BDU router is basically concerned or responsible for routing of PDUs from higher layers to lower layers. A BDU basically is, let's say, the most atomic way or a way to encapsulate a group of data that's needed, either sent or received by higher level applications. And to be able to route this BDU across different layers, basically you have to define the role of each layer and what's exactly how exactly it passes this BDU to the lower layer. So the BDU, you'll find that it has different names to it. You have an iBDU, and this basically used for the data exchange of modules directly above the BDU router. And below the BDU router, you will see low-level modules like the CAN interface itself. The CAN interface, what's meant here by the CAN interface driver is that it's responsible for transmission transmission and reception of LBDU. LBDU means that's the lowest level version of an iBDU. Basically, it is the data link version of the BDU, which is directly received or equivalent to the BDU or the bit stream of bits that's sent or received by the controller itself directly from the bus. So if you need to have a raw frame sent on the bus, if you just copy and paste it directly in the controller memory, that would be an LBDU. Each LBDU or each BDU somehow is processed within the layer, the corresponding layer, and some pieces of information either added or extracted depending on the transmission mode and the transmission direction. So for example, if you have some higher level components here residing above the communication stack, and such high level components are interested in a group of signals, what happens usually is that these I signals are grouped together inside one single iBDU, and this iBDU will then be maintained by the communication module. Communication module provides communication services to higher software components in the AUTOSAR. And this COM module, then, when it wants to transmit these signals on the actual CAN bus, then it will use the services of its lower layer, and in this scenario, specific scenario, it will jump directly to the CAN IF here. But in other scenarios, if the BDU is a little bit if the BDU exceeds the size, the maximum transmission unit of the underlying physical layer, then it needs to be broken down into multiple pieces. And that might be the case that the BDU will be routed to CAN-TP first to make some transport actions on it. In this way, it will be basically fragmented into multiple pieces. But if the BDU fits exactly under 8 bytes, for example, for the single CAN frame, then it will be processed directly in the CAN IF layer. Otherwise, it can be broken inside the CAN-TP, and so on. So that's the overall mechanism that legacy communication technologies used in AUTOSAR before the Ethernet was adopted in 421 specifications. If you look at the Ethernet, somehow the Ethernet communications is using a different scheme. So communication over the TCP stack actually socket-based, not BDU-based, as compared to CAN or FlexRay. And this socket-based communication means that whenever you have two ends, two application ends wanting to communicate with each other, they are only able to do this by means of sockets. Sockets basically is a logical combination of an existing network endpoint, which means an IP address, and a high-level application endpoint represented or bounded to an existing port. So through the combination of an existing port and an IP address, you're able to open a socket, and once you're able to open this socket, you're able to listen to incoming requests, for example, from other clients. And once you listen and accept such requests, you're able to establish communication. And of course, there are a few famous socket types like TCP sockets and UDP sockets. And TCP socket basically is service oriented, in which communication handshake happens first, and you have to basically follow a certain sequence to try to open and close the sockets. UDP is connectionless. There is no handshake required, and it's also possible to make what we call as broadcast or multicast requests using UDP. So you're able to establish one-to-N communication from using UDP requests on the network, which means basically that one server could make a broadcast request over UDP, and multiple clients are able to receive such request and process it. However, in TCP, it's only one-to-one. And this is basically the way Ethernet communications happens in standard Ethernet stacks. And of course, some of the famous transport layer protocols used are TCP and UDP. These are the only protocols actually used. And as for the network layer, there are IP version 4 or IP version 6, depending on the usage of MAC IPs in your network. As for the data link layer and the physical layer, we will try to cover shortly to see how they actually contribute to overall Ethernet communication. But the takeaway from this slide is that the Ethernet world doesn't understand BDU communication. It's only understands socket-based communication. So we need somehow to bridge the gap between these BDU-based and socket-based communication, and that's where the the socket adapter comes into the picture. So socket adapter is an AUTOSAR module here that was placed above the TCP stack. So if you look into how look into the communication path of specified for Ethernet communication in AUTOSAR, you have the Ethernet driver. This is basically responsible for transmission and reception of physical frames on the bus. And then you have the Ethernet interface, which basically reads data link frames immediately received from the physical layer, and then it can pass it to the TCP IP stack or other higher level protocols if needed. And once the socket information is extracted from this frame, then here comes the socket adapter into the picture, because the socket adapter is mainly needs to create an interface between communication service modules using the BDUs, for example, and TCP IP stack. That's its main role. So it basically will map BDUs to sockets and vice versa. So for example, let's consider this. If a software component here needs to send some data on an Ethernet frame, okay, or either Ethernet, you have to go through the COM, and once you update the signals through the COM standard APIs, the BDU will be routed to lower layer through the BDU router, and then once it reaches the BDU router, then it will be forwarded to the socket adapter, and the socket adapter will basically pack this BDU here, as you see here, inside one big Ethernet frame. Of course, it would be a much more overhead to map one single BDU to an entire Ethernet frame, because the BDU size to begin with could be less than 64 bytes, which is the minimum Ethernet frame size. And this means that you would have an overhead or wasted bytes and bad utilization of the Ethernet bandwidth. To overcome this issue, the concept of BDU grouping or BDU container was specified also in 421 AUTOSAR specifications, which gives the socket adapter the capability of packing multiple BDUs into one single frame. And this happens actually, or this is made possible by binding multiple BDUs to one single socket, which is used by one single application endpoint. So in this way, you're able to add as many small BDUs as you need, but you have in parallel to use an ID as part of a header to give some pieces of information to the higher level applications where exactly to put this BDU. So this acts as a sort of ID identifier to be able to map the BDU data correctly to its corresponding signals here in the higher level COM module. And this, as I said, have the benefit of eliminating any communication overhead that may result of usage of small size BDUs. All right, one other concept, a very important concept actually, that's needed to establish Ethernet communication is service discovery. Service discovery as a concept means that that every communicating nodes on the bus, either a provider or a consumer, should have a way to declare its communication needs to other nodes. So, for example, at the server side, early after startup, it starts publishing its service offers for other nodes on the bus to see. So that every other interested client, if requiring this service, should be able to subscribe to it. And from the client side, if you need a specific service, which means that your higher level functions would not be able to continue as expected unless this service is provided to you somehow from another server, then you have to send find requests on the network until you receive a response from one of the service providers. At that point, you stop sending the find requests and you use the data or the received data directly. Why is this established? This is established to try somehow to this is established for two main purposes. First, we need to send. This gives the communication partners a flexibility or a way to send and receive data only when they are needed. Okay, so the Ethernet bus will not be overflowed with information that's sent periodically, for example, while no one else is needing it or listening to the bus, which is the case, by the way, in the CAN or FlexRay, because since it's broadcast medium, any node on the bus, if it wants to send information or a piece of information to one single node, all other nodes on the bus have to listen. And you have to keep the physical medium busy until the transformation process completes. This is not the case here. Since this is service oriented, there will be only communication when a service need use case is present. So whenever receiving a message is required, then the client raises the request. Whenever a server have an actual or something to offer, then it will send the offer request. And the way that the different phases, the way that this process is done also in different phases. Early after startup, as you can see, the find and on offer requests are sent with interleaved periods, and these periods are the delay between these periods is increased also. And the main purpose behind this, or the main benefit, is to try to not to send bursts of Ethernet frames on the bus early after initialization. So this tends to try to minimize the overall Ethernet bus load during initialization or startup phase of the ECUs. So this is how service providers and service consumers in the Ethernet in automotive architecture are communicating to each other. Of course, this way of communication is only meant to try to agree on what kind of services to be consumed or provided, but eventually the actual transmission happens either different data path. So requesting a service or subscribing to a service means that the client will put himself in a state that's ready for receiving the actual data from the server. So basically what it does, it enables or disables data paths which are pre-configured in the socket adapter layer. As we mentioned earlier, the socket adapter is responsible for mapping the BDUs, which might be offered from the server in this case, to be routed down through the TCP layer and to be eventually transmitted over Ethernet frame. So if the server side, for example, tries to send some offers and no one subscribes to it, so it will not enable this data path, which means this data will only reside at the server side and will never be present on the Ethernet bus. And this is basically service-oriented communication. Okay. Let's have a look at the automotive physical layer. As mentioned earlier, currently there are multiple supported physical layers for the automotive. We have 10 base T1, we have the 100 base T1, although the 100 base TX is widely used in automotive application. TX, of course, it's not automotive physical medium, it's a standard 100 base TX using twisted pair cable with multiple channels. But this such connection is mainly used for diagnostic purposes, and it's provided and supported by most Ethernet devices used in automotive. We have also the 1000 base T1, and as we have seen, we have also specifications, maybe not directly listed here, but we have specifications for the 2.5, 5, and 10 gigabit per second. So we are able to establish such high speeds in the inside the vehicle using only one single twisted pair. If you look at the picture here, this is how the Ethernet twisted pair one single twisted pair is built. Basically, the PHY is able to encode and decode information in both directions over this one single pair. And this, without digging into details or related to the electric and how this is established on electric level, this is done using some sort of modulation, amplitude-based modulation, to be able to send both the TX bit stream and receive the RX bit stream simultaneously on the same pair without any corruption of the data. And this involves, just give you a quick idea, involves some initial procedure. For example, the sender have to sense the bus first and sense like some sort of predetermined or pre-configured coding bit stream, and the receiver will listen for this bit stream, and using this bit stream, it will be able to calibrate its coupling circuits to be able to identify the TX stream from the server. And this is done vice versa as well. The receiver starts sending its bit stream initially at learning phase, and after this learning process is established, then the link is up, and both ends can send bit streams in a full duplex way. This is not the case for standard, for example, 100 base TX PHY components, which put the transmission and reception in two different channels. So this is done in a simplex way. However, in the automotive, it's done in a fully duplex way over one channel. And in both cases, in case if you're wondering, because if you compare this to standard low-level communication protocols that some of us might be familiar with, like SPI and so on, there is no dedicated line for a clock. So what drives the line here is mainly the bit stream itself and the changes of the signal level. So the receivers, both the senders and receivers, have to continuously synchronize their clock using this bit stream of data. Excuse me. And prior to communication, They have also to auto-negotiate on the rules each node will play, whether being the master or the slave, and the difference and the speed they are going to use during communication if both ends support different speeds. So this is all done on the physical layer with no interaction to the software. All right, when we look at the standard OSI model, which is, of course, grouped into seven specific layers, starting from application, presentation, and session, down to the data link and physical layers. This is where the most of the standardization done by the IEEE task force lies in this area. So we are mainly putting specifications for different physical layer and data link layer. And when it comes to Ethernet, as we said, the main advantage is that we now have the capability to establish communication over different physical mediums using the same frame format. This is the strength really of Ethernet. So a standard Ethernet switch could have, for example, 4 or 5 ports. One port could be a broader reach physical medium. Another port could be 100 base TX, which is not an automotive compliant PHY. But all of them are using or abstracted on the physical layer level, but the data link layer is common across all of them. The data link layer actually has 2 separate sublayers that we will discover shortly. It has a medium access control, and this is mainly responsible for the addressing scheme inside the MAC, and it has a logical link control that's responsible for controlling the link status with the partner. The switch also has an important feature the LAN networks contributors, because if you think about it, the switch could be, or one specific LAN could have high bus loads due to certain type of traffic. So to be able to minimize and control the traffic load due to different types of features or applications, you could assign easily VLANs inside the switch to try to segregate different types of traffics. Okay, let's have a closer look into the addressing modes supported by the switch. So the addressing modes mainly would be one of 3 modes, either unicast, multicast, or broadcast. The switch operates basically by a learning process early after initialization. So let's consider the following scenario. If you have 4 different nodes connected to different ports inside the switch, for example, you have a node with a MAC address connected to port 1, you have MAC 2 connected to port 2, MAC 3 to port 7, and MAC 8 to MAC 4 to port 8. Initially, the Ethernet switch, when it receives a request coming from this node to send a packet to a destination address, for example, it happens to be MAC 2. It doesn't know exactly where MAC 2 is connected, so it has to figure this out. What it does actually, it publishes or broadcast, or what we call offloads this frame to all the available ports. And later on, when a higher level protocol is used to retrieve the destination MAC address, then the Ethernet switch can easily learn the MAC address assigned to each port through the incoming frame. So, for example, when you receive an Ethernet frame from this node, it has a source address with a certain value. then the switch immediately starts building its MAC address table by assigning the MAC value, the received MAC value in the source address, and assigning it to port 1, and so on. When it receives another request from another port, then it assigns the source MAC address to the port. And over time, you will have already established the full list or the full MAC table, so that when a request is sent from node A to node B, then it will be immediately forwarded only using these two ports without affecting other nodes. So broadcasting is used primarily during the learning initial setup phase or learning phase by the switch, and it's usually accompanied by the utilization of high-level protocols, for example, the ARP, to try to resolve the lower level address of communication partners. But it's associated also, it might be desired at some points to try to broadcast a certain piece of information to all communicating partners in the LAN. So this is called a broadcast addressing. And there's also somehow in the middle way of addressing, which is multicast. And this way, a certain node would be sending a request that only a group of nodes on the same Ethernet is interested to process. And this happens mainly by means of configuration both in the switch and the communication node itself. So you have to configure the Ethernet interface or the transceiver itself to which MAC address or multicast groups it should listen. So for example, if node 4 and 3 are configured to listen to multicast group A, for example, if this node sends a request over multicast group A, only these nodes will receive it and process it, but this node will not receive it. So this is also a different way to try to control the overall network traffic, and this is done. I mean, the switch plays an important role into this. And as mentioned earlier, it's not necessarily that each node here communicates using the same physical speed on the physical medium. Actually, the switch, since this is switched network, so each link could have its own speed. All you have to do is that the node communicating partners here, the transceiver at this node and the transceiver assigned transceiver inside the switch, need to agree on a speed link and duplex mode of operation, and that could be totally independent from other links. So you could have basically, typically, different link speeds. But during the network design, of course, you have to take in consideration that all link speeds are in place in a way that would not cause any traffic overriding or package to be dropped, frame drops. Because if you have a link speed, a weak link in your network that's only able to process data in a much lower rate, and you need to send data from this node to the another node through this weak link, then there is a possibility, excuse me, and there is a possibility that the weak link will drop off or drop out frames. It's also possible that the MAC be configured to block for security reasons or for any reasons. It's possible to block communication over certain nodes or certain MAC addresses, and this is done through the MAC filtering. And in the automotive world, it's really wise to limit communication between different parties inside the vehicle. So it's a common use case or common practice to configure your MAC address during either a software update process, perhaps, or during the initial startup phase, so that the switch would only accept the traffic from predetermined ports and within also the allowed MAC addressing list. So this MAC address table could be either learned automatically by the switch, or it could be pre-configured and loaded by another ECU manager or ECU that controls the switch, or it could be a combination of both. Actually, you could have part of these MAC address tables configured as a static, and the other learned dynamic in runtime. And it's also possible that you, although it's not really practical for Ethernet use case, but it's also possible to configure some edging timers for these MACs, which means I will only accept or assume that the MAC exists in this port for a certain period of time. After this period has elapsed, or time has elapsed, then the MAC address starts to age out, and the Ethernet switch has to learn again this MAC address when it comes through when Ethernet frame comes through the port. Then the Ethernet switch needs to learn this MAC address again. Right. Another important aspect of, or feature of a function of Ethernet switches, which is also done on the data link layer, is the VLANs. The VLAN, as mentioned earlier, is a way used to segregate traffic across the network, and it enables frames of different virtual networks to be kind of artificially apart. So, for example, if you have here a traffic that's assigned a specific VLAN, first let's have a look at the standard structure of a normal Ethernet frame. The Ethernet frame is defined as follows. It has some preamble and some predefined gaps on the bus, and this basically consumes like 8 bytes. And then you have the destination MAC address. This is 6 bytes. Source MAC address, 6 bytes. And then you have the length, 2. And then you have the data itself, the payload, and then the last 4 bytes for CRC. Optionally, you could induce or insert a VLAN tag after the MAC address, source MAC address. And this VLAN tag would consist of the following. It would have some information related to the priority, which is somehow gives classifications for the type of traffic being sent here in this frame. This is priority code point. And there's some other fields, for example, the VLAN ID, if this is a VLAN tag, and if this is an IEEE compliant VLAN tag, then it has to be to have a specific type of identifier. And what's important here, to be able to distinguish between the length field and the normal VLAN field, their value ranges have to not overlap. So it has been also standardized that the standard frame length must be lower than or equal 1,500 bytes. If the value received here is bigger than this value, then this means that this is a special field which will be interpreted by the receiving node as a VLAN tag. Okay, so what does a VLANs again? What benefit do VLAN tags bring to the Ethernet switching? We can consider that any network, for example, any network interface can be put in some sort of promiscuous mode, which means that all the traffic entering this port could somehow be copied into another port, right? So somehow it might not be desirable to have such information to be passed out outside the the communicating partners. So in this way, you can put all the communicating partners traffic inside one single LAN, right? That would be an option, and not to let any traffic of the LAN. That would make sense, of course. Another use case for usage of VLANs is that some LANs are heavily used than others. And when you consider, or not to put it in the right way, not some LANs, some modes of traffic or some types of traffic are heavily used than others. And it just might be desirable to try to distinguish those traffic frames by assigning a specific VLAN tags to them. And that VLAN tag could be used to try to alter somehow the way this kind of traffic is processed inside the switch. So for example, you could assign a high priority for such traffic, and that's when the Ethernet hardware itself will give it high priority compared to other frames. So the VLAN tag, it's not only understood by the Ethernet switch to try to direct traffic based on the receiving ports, but it's also possible to affect the way the frames are queued inside the switch and giving them high and lower priority. So this also has direct applications in this area. One other security concern also that's come into my mind is that when you, of course, as we discussed, most LANs support broadcasting, and many upper layer protocols above the TCP use this feature extensively, especially if they wanted to communicate to an IP which is not already known to the partner, or the MAC address of the IP is not known, so you need to learn it. So you can easily understand that as more and more LANs gets connected together, okay, maybe using an intermediate device, a router, the number of broadcasts passing through the Ethernet switches would be hugely increased in size, and this could easily jam up the entire network. So to prevent this, you could actually not or isolate the scope of these broadcasts to the respective VLAN. So for example, if you want to send a broadcast request to all nodes communicating or that belong to VLAN 2, only the nodes that belong to VLAN 2 will receive this broadcast requests. So other VLANs will not receive it. This is also one important feature to understand about VLANs, is that they tend to somehow segregate or isolate the contributing nodes from the rest of the communicating ports over inside the switch. Of course, there could be some advanced rules configured to bypass traffic from one certain VLANs to VLANs, but that's outside the scope of this session. But it's also possible to do a lot of actions, ingress and egress policy actions based on this VLAN. All right, so in automotive, let's have a look at what kind of architecture is possible to establish when it comes to utilization of Ethernet and Ethernet switches as devices that lie in the heart of Ethernet buses. We have basically three different combinations or hardware configurations. Either we have a microcontroller that has the switch embedded inside it, and excuse me, give me 1 minute. Right, either we have the switch embedded inside the microcontroller itself, and the external PHY, which brings or supports communication over the physical medium, is located outside the switch, which means the switch needs to control and connect to the PHY using a management protocol. That is one possible configuration. Another possible configuration is that the switch, and by the way, the switch itself could still contain the PHY even if it is embedded inside the microcontroller. That also might be a possible scenario. Another possible configuration is that the microcontroller doesn't include the switch. Excuse me. Another possible scenario is that the microcontroller doesn't include the switch embedded inside it, so it has to be placed outside and then controlled by the microcontroller using a communication protocol. That could be SPI, for example, or another management protocol specially dedicated for controlling transceivers and switches, which is MDIO, management data input output. So in this way, you have to control and manage the switch externally, but the switch in this case could contain the PHYs internally. And it's also possible to have PHYs embedded inside the switch for some of the ports, but some of the other ports might be left for extension with the needed PHY medium. And the last configuration would be a microcontroller that doesn't include or embed the switch inside it. And the switch itself also doesn't include the PHYs. So the microcontroller in this way have to manage both the switch and the PHYs. So it has to first configure the switch and manage it using any communication protocol. And the underlying PHY that's connected to the switch can be managed either directly by the switch itself, if it has a direct MMI interface to it, or it could be alternatively managed directly by the microcontroller itself. All of these scenarios are widely used and common in the automotive. All right, so when we step a little bit back to have a look at the standard or usual higher level protocols used in Ethernet outside the automotive world, we'll see a number of high level communication protocols, starting from the HTTP, the famous protocol, of course, used to communicate, that everyone uses in his browser, TLS, transport layer security. This is how you establish or make secure connections with the servers over HTTPS, for example, protocol. You have some high presentation layer protocols, network discovery, or domain DNS. This is to translate the domains and the IP address, and so on. The IP stack is rich of protocols that most of them actually don't have a direct use case in the automotive world. And as we will see shortly, we only adopted in the automotive a subset of these standards into the Ethernet stack. So let's have a look at it into this. These are the major automotive high-level protocols when you try to map them to the OSI layer. So in the field of normal communication over Ethernet, you need, as we described, service-oriented communication, which happens using sockets. And the sockets, as we mentioned, needs to be mapped to BDUs. As we will see later, see shortly, these BDUs basically come from higher level data structures and needs to be serialized. So we have some way of serializing this data using SOMEIP protocol, and we in combination with the service discovery. So this area here is used for basically communication of normal Ethernet frames. When it comes to diagnostics, we have specialized standards for this, diagnostic over IP. For the XSP, also we needed to extend the XSP operation either over the data link layer of Ethernet and physical layers. For the address resolution protocol, this is responsible for mapping of IPs to MAC address when during the learning phase or during the time the switch tries to build a MAC address table, as we discussed shortly. And this is only done or operates in IB version 4. The equivalent or what's compatible with IB version 6 is network discovery protocol, but it's basically serves the same function. And we have an entire stack that supports the different standards, communication standards related to audio-video bridging. And this is mainly serves the infotainment and multimedia, or maybe sensor fusion when it comes to dealing with high sensitive pieces of information and assigning timestamps to them and so on. And then we have an entire stack related to smart charging, which is governed by the ISO 15118. It has different parts, of course. The physical layer here is specified in part 3 of the standard, and it's mainly established using power line communication. And the higher level protocols are specified in part 1 and part 2, which basically cover all of these areas combined. So these are the most areas where higher level protocols over Ethernet are used in application in the automotive. Okay, I want to shift the focus now. If we try to break down the last slide into specific use cases, so let's have a closer look into how service-oriented communication actually is established in the in Ethernet stack. We mentioned earlier that we needed to establish a mechanism to for servers and clients to negotiate their services and request and find and declare their service states needs. So this is the job of the service discovery. We already discussed it. This basically enables and disables communication paths here only when needed. But assuming that the communication path is already enabled for a given PDU, for example, then how the data is actually transmitted from the higher level software component down into the lower level communication layers. As you might guess, the Ethernet, of course, its power comes into sending huge amounts of data in short amount of time due to its high bandwidth. But at the same time, we need to find the best strategy possible to be able to handle data that's somehow not will not be transmitted on the network level in a very efficient way. For example, if we have a higher level structure data that contains, for example, characters and other data types. Some of it is primitive, other types are not primitive. Usually, when you map such data types into internal memory inside the microcontroller, you will see some padding inserted by most of the compilers, or due to network type alignment constraints. So if you take the data structure as it is and try to compress it and send it on the network, you will have multiple issues. First, you will have padding or reserved space sent that could use the network bandwidths. Okay, so it's a waste of bandwidths. More importantly, there is no guarantee that this data, if sent this way as it is, it will be interpreted correctly by the other side or the receiving side, because the receiving side could be operating in a different NDNS, for example, and it could have a different memory layout, so the data would be for sure misinterpreted. So we needed to find a standardized way to pack and unpack the data, and that's where the SOMEIP comes into the place, it comes into the picture. Before sending the BDU, we need first to serialize it, and this is done by adding some additional piece of information in front of each BDU that's being set or transmitted by higher level application. And this piece of information basically gives some identification about the message that's being sent, or the BDU, the overall length of the message, and some additional information which related to the version of the protocol being used, so that some sort of sanity checks will be done by the receiving side as well, to make sure that we are sending and receiving data using the same frame format. And using this message ID, basically each of the sender and the receiver will be able to uniquely handle this piece of information in the correct way. So you will be able, for example, to eliminate these padding bytes by concatenating all of this data directly, concatenated next to each other, and you will be able to generate a homogeneous and error-free bit stream of data that is that's sent on the network and successfully received by all intended parties. This is mainly the purpose of SOMEIP module, and this is, as you can see in the picture, is automatically integrated in the AUTOSAR layer as part, or let's say in parallel to the RTE. So the RTE will be able to detect any transmission or reception requests from higher level protocols, and it will automatically trigger the SOMEIP transformer to serialize and unserialize the data depending on the direction of communication. This is the role of SOMEIP. We have also a major contribution or important role that Ethernet needed to extend when it came into the picture in AUTOSAR back in 2014 as part of 4.2.0 specification, which is UDP network management. Network management as a concept It's not new with Ethernet, of course. It is well established before the Ethernet was introduced into AUTOSAR. And the main idea behind it is that we need to find a mechanism to keep a certain cluster, an Ethernet cluster in this case, to be awake only when needed, and to be able to coordinate the shutdown and wake up activities across all the nodes. And this is basically as part of some efforts to try to minimize the overall load or power consumption inside the vehicle. So whenever all of the nodes inside a specific cluster are no longer in active communication with each other, then there is no need for them to be active. Then they will enter into coordinated shutdown or wake up. And this is done basically by specially formatted frames or NM packets, for in the case of Ethernet, that would contain some information regularly sent by all communicating nodes in a certain Ethernet cluster. And this information will contain the ID, for example, of the node, some pieces of information that would signify if the node is ready, if the coordinator, NM coordinator, which is a master NM coordinator on the bus, ready to sleep or not. And this would basically signal to each of the slave nodes in the bus that no other node is requesting communication, and they will enter into a coordinated shutdown sequence. That's basically the main benefits of incorporating or supporting this network management setup over Ethernet. Another important application of Ethernet in automotive, of course, is XCP. XCP is stands for X here is like a generic calibration protocol. It's actually used for calibration and management of data. Calibration concept, as you might be familiar with it, is mainly related to the usage or manipulation of certain pieces of information in ECU memory to try to measure or calibrate the software behavior. So usually when you design your software, you put some pieces of variables that have direct effect on the behavior of software. So for example, you have some constants that select different variants inside the car or different configuration parameters. You might also have some values that specify how the imager inside your camera react to certain degree angles and so on, and how they process the overall image. So such parameters usually needed to be tuned to produce the best result. That's one way. So in this case, you need to calibrate the overall software performance. And in other way, you could already have some variables located in global memory, and these variables represent some internal states inside your vehicle or some overall conditions that you need to check to be able to debug and troubleshoot issues. So whether for calibration or measurement purposes, you need direct access to some of the software elements which lie in your memory. And that's what the XCP protocol mainly comes into the picture. It tries to provide some access to these elements by building data acquisition arrays, by packing all of these data together using specific format and sending these data acquisition lists over the whatever the underlying network topology, Ethernet in case of the Ethernet, or CAN or FlexRay. Also, they are XCP supported over this network also. So these data acquisition lists will be sent to a communicating node. It could be any switch that would receive this automotive or translate the physical layer of Ethernet into another format that could be, for example, imported into a measuring or monitoring tool. So basically, you need a media converter to translate this automotive traffic over the physical medium into standard Ethernet traffic, or other, maybe it could be a USB, for example, if the monitoring tool resides in the software. It interfaces with this box using USB or Ethernet. So the main idea is that you receive such data acquisition lists and you make whatever measurement or calibration activities and overall analysis activities on PC. So this is the main usage of XCP, and that's why extending the Ethernet to support XCP was very important, which is already well established in recent versions of AUTOSAR. Another important application of Ethernet is what's known as the time synchronization. And this is part actually of audio-video data transmission in general. So the audio-video bridging in general, that's a common name for a set of technical standards which provide improved synchronization, low latency, and reliability for switched Ethernet networks. So it embodies actually a number of substandards. For example, it embodies the IEEE 802.1 AS. Okay, this is a substandard that puts some specifications for communicating partners to be able to maintain timing synchronization for the exchange traffic. And this is, of course, the case for time-sensitive applications. Whenever you have a distributed vehicle function across multiple ECUs, and the decision-taking in one of these ECUs is heavily dependent on the reception of real-time input from the other ECUs, so you have to be able to make sure that the traffic is received within this time constraint. Otherwise, the information being received might be out of date, actually, and you would be taking wrong actions. So that's why it's called time-sensitive applications. So synchronization, the time clocks or time domains across multiple nodes is standardized as part of this IEEE substandard. And there are also, as part of the audio-video bridging activities, there are also multiple substandards, for example, that control how forwarding and queuing of time-sensitive frames should be done inside the switch and in software. This is also standardized. So this is a huge, a very important area where Ethernet comes into the picture and plays a very important role here in this stack. And there are, as mentioned earlier, we have some dedicated stacks to cover the functionality or higher level functionality depending on these communication protocols, which are standardized here. Switch management in general, yeah, that comes as a byproduct due to the complexity of the software components. There needs to be some sort of getting more insight into the switch itself to be able to understand what kind of traffic is being transmitted and how the overall network behavior lays out in runtime. So you might be interested, for example, in for diagnostic purposes to mirror or some you could say sniff out all the frames which are being switched into a specific destination into a diagnostic port. Usually when a communicating node, let's say this node, sends traffic to another node, this traffic will not come out outside the switch in any other port. That's the main advantage of the switch, right? It has multiple collision domains and it uses dedicated switch links, so the traffic will not cross any other ports unless the intended destination. But somehow, for diagnostic purposes, you need this traffic to be available in other ports. So it's also always possible to put the switch in this diagnostic mode by configuring some advanced features like port mirroring, for example, which is basically means you mirror the traffic coming out or inside a specific port into another destination port. You could also try to simulate traffic coming inside one or more ports, whether actually they are not receiving traffics, right? So this means isolation and simulation. You try to simulate specific scenarios, maybe some faults in runtime. Maybe you try to cut off specific ports, disable them in runtime, and see how the other nodes would react. or maybe you could try to isolate some ports from the rest of the network and instead introduce some faulty traffic and see also how this overall system would react. So the Ethernet Ethernet switches provide some advanced means which could be used for the software validation, not only for the software development. Okay, so one of the major and most important applications of Ethernet is, of course, the vehicle-to-grid communication. Vehicle-to-grid communication, just to give you an idea, what does this mean? It means that when you think about, of course, this is applicable only for electric vehicles. So when you think about electric vehicles, what comes first into mind is that you have an electric vehicle powered by a battery, and similar to any battery powered device, when the battery runs out or be almost empty, you need to recharge, right? This is the main or easiest assumption. So there should be charging stations and some standardization for the cables and the connectors used to connect the car, and the direction of energy flow by default should be from the vehicle, from the grid to the vehicle. But here is what the vehicle to grid tries to change. The vehicle to grid technology tries to makes it possible to charge the electric vehicle battery, okay, in one direction, and take the energy stored inside the car's battery and push it back to the power grid in the other way. So this bidirectional charging is made possible and synchronously depending on some overall conditions. So for example, when you have some let's call it for now some good initiatives or grid conditions, then the grid would supply the energy to the vehicle, right? And in other conditions, when the grid is loaded somehow, or when the battery status is more than sufficient to do the planned trip, then the batteries of the vehicle itself could start supplying the grid with energy back. This could happen due to some rush hour times, for example, where the energy load is high during specific time of the day, or it could happen that, for example, that overnight there was an overall surge of energy demand, and the vehicle or the grid communicated with the available energy vehicle fleet so that they could supply this excess energy demand instead of going for a backup battery saved energy, for example. So overall, this model tries to provide the best consumption level, either from the grid perspective or from the car perspective. So, and doing so, this gives you the best possibility or opportunity for energy optimization, right? Because you can charge the vehicle at the cheapest point of the day, whenever the energy load is the most suitable. And it could also give you some give you the alternative to potentially move to other on-sites where electricity demand is cheaper, right? So basically, this turns your electric vehicle fleet into an energy storage asset. And instead of treating it as energy consumer only, it treats your energy battery powered vehicle into an energy storage asset. And you will get also some money from feeding back the grid, not only from consuming. So when you consume, you pay some money. When you feed the network, you also get some money. And there are a lot of several business models on top of this vehicle to grid technology related to the subscription models and so on. And it's all governed as part of the IEEE 15118. And how's this overall related to Ethernet? I mean, this overall concept is mainly involving direct exchange of energy, over coupling direct DC charging couplers or AC charge connectors. But where the Ethernet actually comes into the picture, Ethernet provides the backbone for smart communication or smart charging, because the connection itself that's established, between the vehicle and the charging station has what's called power line communications channels. And over this power line communication, you are able to send both analog and BLC encoded or Ethernet encoded data frames over this power line communication. And that's why this smart or V2G charging standard uses a different physical layer than the standard Ethernet physical layer, or even the standard automotive physical layer. So it mainly uses power line communication, where it encodes both the analog and Ethernet frames used for exchange of information and agreement on, for example, the charging profile, the charging load and capacity between this all has to be agreed between the vehicle itself and the charging station. So Ethernet provides the backbone for establishing this communication. In the recent versions of this standard, by the way, it's also possible to perform charging over wireless power transfer. This would be this is already supported in the recent versions of this standard. And it's not only limited to personal or road vehicles. It's expanded actually to include airplanes, trains, buses. It includes every moving wave of transportation to be able to supply the grid back. Right. So I think that's kind of covers most of the major or big contribution of Ethernet to vehicles in modern defined or software defined vehicle. Let's try to quickly have a look into the future and how the industry leaders are putting some expectations for the overall vehicle architecture to expand and grow in the future. If you think about it, if you analyze the current situation, actually, this is the current. This is how the vehicle architecture look like today. Mainly, it is revolving or centered around one big central gateway, and this central gateway has different for different physical layers and multi buses. And whenever you need to take some information from another typical physical domain, you have to establish this cross-functional connection. And as you can easily imagine, when the software functionality grows more complex, then these sub-buses tends to be more and more loaded with communicating nodes, and the baud rate limits of the underlying typical physical layers tend to reach their limits. And this is where most ECUs or vehicles architectures are defined today. But we started to see a major shift towards two different architecture patterns. One is which are known by the domain-based architecture and zonal architecture. So in the domain-based architecture, the trend is to try to put more and more centralized domain controllers, as we discussed earlier, that are responsible for having the overall software functionality and offloading the low-level functionality to local controllers. So in this way, it's we have eliminated the software split or functional split on the higher level to be contained inside one domain controller, and this makes the software maintainability on higher level executive functions easier to maintain. That's one major advantage. And if you think about it, also it has direct implications when it comes to cost, for example, because you have minimized or consolidated the software functionality in one place, so the software validation efforts and verifications cycles will be much shorter and will be much more cost efficient. Another trend towards the toward the movement of zonal architectures. Zonal architectures here is a completely new concept that is expected to try to prevail beyond 2025. And in this concept, the main shift is towards usage of very few multi-purpose generic computing platforms that will host multiple domains side to side virtually. So instead of grouping all the related software functionality under one domain, which still requires higher meshing to some degree, I will try to distribute these zonal ECUs to make all the processing needed inside a certain part of the car. For example, if we have certain sensors or actuators located in right side of the vehicle, close to the passenger seat, then we will put a zonal computer architecture computing platform there, and this platform would take all the inputs from all the actuator sensors in this area of the car, and this input will be processed processed separately depending on the intended functionality. So these zonal architectures should somehow provide a means to isolate the software functions that belong to different domains, and that's where the zonal or the name virtual domain controllers comes into the picture. In this way, you have completely changed the way software is coupled to hardware. So you have basically provided a generic hardware architecture that would be used to host any software functionality, and you have pushed for more complex and high computing power inside these generic computing platforms, because they will basically host multiple virtual machines, for example, to isolate different functions inside different domains in the car. And there would be still the need to communicate information across these zonal computing platforms, and this would basically done this will basically be done via an Ethernet backbone inside the vehicle to establish the needed high baud rate or high baud transfer rate, of course. So as we can see, Ethernet is in the heart of the vehicle architecture, whether in the coming generations that we'll start to see shortly within or before 2025, or even beyond that. So if you think how far or how close are we today from reaching such architectures, I here provide an example of a commercial product that's already available in the market today. This is from NXP 32G family of controllers, and they are actually provided in the market. I mean, they are marketed as zonal controllers, so they are specifically produced for this purpose. If you look at the processing power of such controller, it includes 4 Cortex M7 controllers, it includes 8 Cortex A53 controllers, and includes 20 megabit SRAM, which can be extended using an external SRAM interface, of course. And it includes most of the classical and modern peripheral protocols that you ever need in any domain controller or even zonal ECU. So CAN, FlexRay, SPI, LAN, all the classic protocols. And even I personally worked on one of these controllers. They contain even some low-level communication protocols like PSI-5, for example, peripheral serial interface, which is widely used to communicate with high sensitive applications like airbags, for example, airbag sensors. And these controllers come with the hardware support up to ASIL-D, for example. And to facilitate the communication or the split of software functionalities inside this controller, they out of the box try to help you by the capability of configuring these processing bar into a number of isolated clusters. So you're able to configure any arbitrary number of these cores into a specific cluster, and you're also able to map certain specific peripherals to those clusters as if they are running totally independent from other core clusters. So if you put, for example, a software application inside a certain software cluster, it will execute completely free from interference from other virtual machines, maybe, or other applications running on other core clusters. In this way, you are able actually to establish completely parallel domain functionalities inside this zonal ECU. This is just an example of a commercial product that's already existing in the market. So it paves the way easily for the shift towards domain and zonal architecture inside the vehicle that will come in the next generations. Right, I think I'm finished with most of the ports and the points I wanted to cover for today. I will be glad to hear any questions if you have.
Thank you very much, Mohammed, for this comprehensive overview and I think detailed overview. You started with a history of the Ethernet and then discussion regarding the UZI model, comparing it against the AUTOSAR model, and details regarding the implementation of the automotive architecture and how the future should look like. So I think that was a very interesting and insightful presentation. Thank you very much.
You're welcome.
I guess we can look into the question section. Yeah, please.
I should look into the YouTube channel, right? I have not it. I can open it.
Okay, let me display the questions one by one over here. So Muhammad Abdu Muqallad is asking, how is the Ethernet safer than CAN and LAN?
Okay, it's the Ethernet, let's say, safer than CAN and LAN because it brings to the table the already established security standards that is widely used in applications outside the automotive world. So you can easily adopt the TLS, transport layer security, right? Standard, which is used to establish secure connection, for example, with another party to upgrade your software or even encode or program a specific functionality in runtime. Okay, so such higher level communication protocols are coming, are used as de facto standards over the Ethernet communication stacks. This is not widely used or not present in CAN and FlexRay legacy systems, legacy communication.
Okay, thank you. And the next question is from Matt Hodges. I think it's more like a business insight. Which OEM is the closest to full integration of OTA flashing?
Which OEM is closest to what?
The full integration of over-the-air update flashing.
Multiple OEMs are going through this approach. I think I have personally worked with OEMs. Maybe part of them is Cariad, which are considering. Cariad is part of VW Group, considering this approach. But I would not consolidate this to specific OEM. By the way, over the air, we have some already commercial examples in the market. So Tesla products, for example, already perform over the air. Mm-hmm. But the point is, if your question is whether over the air is already established or not, it's already established, right? But whether to do it within the AUTOSAR framework, that's a different story, because over the air, when you think about it, you have to look at it from different perspectives. Over the air, basically, you have a running application, right? And you want to download a software upgrade without interrupting the running application. So in context of classical AUTOSAR, this is a little bit difficult to do compared to adaptive AUTOSAR, right? So the classical AUTOSAR, you have one combined piece of software that's tightly together due to this software architecture. So all of these layers are tightly coupled together, and basically you have one big binary that covers the entire scope of the application. So be able to replace the entire application over the air, that doesn't require only support from software, it requires support from hardware itself, because you have to segregate or allocate like a backup space in the flash of your controller to be able to host the upgrade while it's being downloaded and still being to operate using the existing binary. And somehow at some point you need to switch to the upgrade, and you need to decide if you're going to fall back or not. So what I mean is that in the scope of classical AUTOSAR, this is, I have not seen it done yet. And yeah, I have not seen it done yet in this way, but I have seen targets, for example, from ST, Stella architecture, that support over-the-air updates. Basically, you can combine the entire flash address space into two different combinations. You can configure the address space into one single space for normal operation, or you reduce the address space into half so that each memory cell have like a virtual or equivalent cell, which would be used only for in case of over-the-air updates. So in this way, your flash address space will be able to host two applications in parallel, the primary application and the backup application, which is updated over the air. So this is, the hardware is already capable of doing this, but the software, I cannot give an input into this. I have not seen a full real example that where this was established, at least for the classical AUTOSAR. When it comes to adaptive AUTOSAR, it's a different story, because the upgrade here is not on the it's only in the basic of on the scope of a certain executable or service. So it's the impact and the complications is much more different, right? I hope I've answered your question.
Okay, thank you. And then comes a question from Mohammed Hamdi. I think he's asking about the security aspects for Ethernet, something like authentication, integration of data.
There are multiple security aspects of Ethernet. There has been a lot of standards devised over the year. There is a TLS, for example, transport layer security. This is a standard used to establish secure connections over diagnostics, for example, in automotive today. Before you want to upgrade or download or change any critical parameters in runtime, you need to declare to the ECU that you are an authentic, you have an authentic identity. So there are multiple. Is that there is also secure inboard communication. This is, if you have heard from overall the years, that has been multiple attacks done by geeks who try to manipulate the vehicle harness and try to figure out what is data, how is data sent and how it is processed with the ECUs. So basically, if you have access to the vehicle harness, you can easily sniff or you can try to basically read whatever bit stream of data is being transmitted, and with some brute force attacks you can somehow figure out what is the purpose of this data and how it impacts of the operation of the vehicle. But the security or let's say more security measures has been taken to try to prevent any manipulation in this direction. So there is a concept called secure inboard communication, which means that all frames sent in network topologies inside the vehicles these days are not sent simply raw, containing raw information. They are sent and the what we call a MAC, which is like a hash value, or although it is generated using a cryptographic service, is sent alongside with the data, so that the receiving node is able to clearly identify and judge if this data has been manipulated or not. So the data itself is being sent in a secure way. It is not sent encrypted, but it's sent with what we say like a digital signature attached to it, so that the receiving nodes will be able to receively judge that this data is authentic and not tampered with. So the security of data communication is enhanced in multiple ways. inside the vehicle.
Okay, thank you. And a question from Mohamed Abdurrahman. He's asking if the SOMEIP is considered as the socket or equal to the socket adapter.
No, some IP is above the socket adapter.
Okay. And we have a question from Ahmed Ismail. He's asking if we have like a router inside the vehicle network. We already have a switch, but do we have a need for getting a router there?
The router, in the sense that if you compare the router to the router that comes in your mind when you talk about open world communication, it is not really needed, because the router basically is a device that routes the traffic from a specific LAN, local area network, into a different LANs. And when jumping and crossing this boundary, you have to do some network address translation. So in this sense, the router is not needed, because its functionality is performed by what's called a gateway. So the same functionality is done if you need to cross the traffic between different LANs inside the vehicle itself. If this case exists, then you will have a gateway and it will perform this functionality. But the actual use case for the router that exists outside the vehicle doesn't exist in the car. So network address translations and higher level protocols related to routing, and for example, SNOOP protocol, which is determining the most optimized routing path. Such use cases don't exist in the car, because at the end of the day, it's a static architecture. I mean, there's no much room for figuring out where to route the data. All the routing paths are pretty much configured during the software design.
Okay, and we have also another question from Ahmed Ismail regarding the configuration of switches. Is it done during the development time only, or remote frames are sent every time the ECU is switched, or or maybe after the production?
All right. So usually there are two ways to do this. Usually, if you decide to manage the switch externally, then the master controller needs to send the configuration data to the switch each time after startup. And this means that during production, these remote management frames, or if the management is done directly using another protocol, for example, SPI, anyway, the management process would need to be done each time during the power up, which means this will happen also after production. This is one way to go. Another way is to flash update or embed an existing firmware inside the switch, so that the switch would configure itself automatically after power up. And in this way, the switch would not receive or need direct management from the main controller, except for during the software update. During a software update, then the management or master controller will send this software update to the switch.
Okay, and another question from Ahmed Said in the same context. So, who is supposed to send the remote frame? Is it a single controller, or all the controllers in the network could do so?
A remote frame for what? Configuring the switch? Yes, it's a single controller. The controller that's responsible for managing the switch. Usually, it's one controller responsible for managing the switch.
Okay. I hope you got the question correctly from Ahmed Ismail. Please provide feedback if I misunderstood the question. And then we move to Muhammad Abdurrahman is asking, is the domain topology equal to the Zoom topology? I think no.
No, they are not equal.
Okay.
I can jump back to it, but it's two different concepts.
Okay.
The domain here means grouping all local controllers that perform related functionality under one single master, which acts as the high brain where the high brain logic inside this domain is being and high level executive functions is being done, and these will mainly perform some low level functionalities, interfacing to the sensors, some reading the data, and all of these local controllers bring or send all the data traffic here, and this is responsible for combining and fusing all the data together and making uh, or developing the model or whatever the control logic will be implemented on higher level here. But the zonal here, actually, each zonal computer, each one of these contains functionalities that is not that resides in multiple domains actually, because here the grouping of software functionality is done. It's not done by the feature. It's done by the positional space inside the vehicle. So
Okay.
basically, you will make one mega computer or platform responsible for processing all the inputs or sensory operations or data or network traffic related to a specific zone inside the vehicle, not mapped by the logic itself.
Okay. Thank you. And we have also another question from Ahmed Ismail asking about the possibility of having wireless communication within a vehicle. I think it's more like
No, no,
yeah, please.
no. I don't think it's. And I don't think there is a need to go in this direction
Hmm. The
because
noisy
otherwise,
environment, PMC.
yeah. No, I mean, it's for me, it's not practical. It's we have we need of course this will bring more and more opportunities for bringing noise, as you said, and as long as the communicating nodes are 1 or 2 meters apart, why should they communicate using wireless? Wireless would be needed to bring some sort of freedom. For example, it would be incorporated in, it might be incorporated, actually, it's already been standardized in the vehicle to grid standard 15.11.8, the dash 20, the newest version, where the charging itself will be supported over wireless. That's a specific use case. Okay, maybe we can consider this, but for nodes that reside in the vehicle body itself, I don't think there is a need to make wireless communication.
Okay, and the last question is from Matt Hodges, and um,
How will implementation of automotive there be a virtual application or VM integrated in the car for diagnostic only? No, there will be an actual VM running on top of a hypervisor. So if you consider this complex platform, there is no way that you would need all of these amount of processing power assigned to one single application. So what will happen is that you will take only 2 or 3 of these cores and configure them together as a network cluster. On top of this network cluster, you will flash a dedicated application or type 1 hypervisor, for example, and on top of the hypervisor, you will put 1 or more virtual machines. This is the actual use case. That's how it will be done. So it's not for diagnostic purposes. It's for actual production purposes.
okay, and Awad Bahid is thanking you for the fruitful session, and also
Thanks.
Hazim Khalid.
Thanks. Thanks, Awad. Thanks, Hazim.
Okay. And I would like to again thank you very much for your time and effort you put in the presentation. And of course, we as a community owe our success and to the dedication and expertise of our volunteer speakers, just as you, and your invaluable contribution make such fruitful webinars possible. Thank you. Thank you,
Yeah.
everyone, for your time.
Thank you so much. Have a nice day. Hope to see you later. Thank you.